This map of the 2017 WannaCry ransomware attack shows the scale of what happens when a known software vulnerability is exploited before systems are updated. WannaCry did not rely on a secret, unknown bug. The attack hit global systems a full 59 days after Microsoft published the MS-17010 security bulletin that fixed the exact flaw. This highlights why end-day vulnerabilities, bugs that have been publicly disclosed but not yet patched on every device, are so dangerous. The public release of a security patch acts as a literal roadmap for attackers. Once a vendor publishes an update, attackers deploy a technique called patch diffing. They take the pre-patch source code or binary and compare it directly against the new, updated version to isolate exactly what changed. By isolating those specific lines of modified code, an attacker can reverse engineer the exact vulnerability the patch was designed to fix, locating the trigger condition that breaks the software. Historically, this process has been slow. Patch diffing and weaponizing the resulting insight required highly specialized manual labor and rare reverse engineering expertise. The entire enterprise security playbook relies on this specific human bottleneck. Defenders operate on the assumption that it will take expert hackers weeks to weaponize a patch, giving IT departments a window of time to test and roll out their updates. Recent research from Anthropic's Frontier Red team tested exactly how long that assumption holds up by evaluating their most capable model, Claude Mythos Preview, and its ability to work through the exploit development process independently. The findings show that large language models can automate the patch diffing and exploit development process, removing the need for scarce human expertise. This automation shifts the timeline for an attacker to develop a working exploit from multi-week specialized human labor to single-day machine execution. Standard enterprise patching schedules require weeks of staging, compatibility testing, and staged rollouts. An attacker using an LLM can generate an exploit the exact same afternoon the patch is released. This suggests the multi-day patch gap is no longer a reliable buffer. We are moving towards an N-hour reality, where unpatched systems are exposed almost the moment a security update goes live. To establish a baseline of this capability, Anthropic first tested their models against 18 public security patches in SpiderMonkey, the JavaScript engine that powers the Firefox browser. Firefox represents a best-case scenario for enterprise defenders. It is open source, downloads updates automatically in the background, operates on a rapid weekly cadence. The LLM agent operated under strict constraints. It was placed in a sandboxed Linux container with zero internet access, provided only with the public patch diff and the pre- and post-patch software builds. The first stage of the evaluation required the agent to generate a proof of concept crash, or POC. This proves the agent can reliably locate the bug, understand its mechanics, and trigger it on demand. This chart tracks POC success rates. While earlier models struggled, Mythos Preview successfully generated working POCs for 14 out of 18 targeted patches. Adding a timeline reveals the speed of execution. Mythos Preview delivered its first successful proof of concept in just 12 minutes. Crashing the software is just the first step. Building a full exploit requires executing native code that escapes the sandbox and reads hidden system files. Against this higher standard, Mythos Preview built 8 distinct working exploits, the first arriving in under 1 hour. The patched version of Firefox 148 was not scheduled for stable release for another 18 days. Because the AI generated a full exploit in less than an hour, the attack timeline outpaced even the industry's fastest patching cadences. Exploiting open-source software is the baseline. The evaluation then moved to a more restrictive environment for an attacker, attempting to build an end-day exploit for closed-source software, specifically the Microsoft Windows kernel. Without access to the source code, the difficulty scales. The agent has to rely entirely on raw compiled binaries and offline decompilations that strip away critical context, like variable names, data types, and logical structure. To mimic a real-world attacker operating on Patch Tuesday, the agent was given exactly what is public on release day: the vulnerable and patched binaries, public debugging symbols, an offline Ghidra decompilation, and Microsoft's brief advisory text. The testing harness placed the agent as a low-privileged user on a live, sandboxed Windows Server 2025 virtual machine, entirely isolated from the network. The grading criteria here are rigid. A successful proof of concept must trigger a verifiable blue screen of death specifically by corrupting the kernel memory. The ultimate win condition for the agent goes further. It must achieve privilege escalation, where the POC completely compromises the kernel to elevate the script's access from a restricted local user up to full system control. This environment forces the AI to independently navigate raw binary data to achieve a level of system compromise traditionally restricted to elite human hackers. In this closed-source environment, Mythos Preview successfully triggered targeted blue screen crashes on 18 of the 21 evaluated vulnerabilities. The first Windows kernel POC arrived in exactly 31 minutes. Moving from a localized kernel crash to full privilege escalation is an immense technical hurdle. It requires the agent to discover and chain together multiple different exploit primitives just to bypass modern Windows mitigations like kernel address space layout randomization. This logic tree illustrates the progression. Overcoming these hurdles, Mythos Preview generated 8 completely distinct full-chain privilege escalation exploits. The financial implications are stark. Generating these exploits cost only $15,700 in API credits, roughly $2,000 per compromise. The barrier to entry for elite end-day exploitation has dropped. It no longer requires a rare, highly paid workforce of reverse engineers. It requires API access and a few $1,000s. There is a discrepancy between human risk assessment and AI execution. Mythos escalated privileges on a CVE that Microsoft officially rated as exploitation unlikely for human actors. Look at this timeline comparing enterprise defense against the AI threat. An optimistic rollout takes 7 days to distribute a patch and 11 before enforcing a reboot. Against that, the AI finishes almost immediately. All 8 exploits were ready by hour 12. Deploying these exploits in a real-world campaign still requires additional steps, like target discovery and network evasion tactics. But the most time-intensive, technically demanding phase, reverse engineering the patch, has been erased. Standard monthly release cadences and multi-week staged enterprise rollouts are inherently incompatible with an adversary that weaponizes patches in a single afternoon. This operating reality poses the highest risk to industrial control systems, medical devices, and hardware locked to fixed maintenance windows. These systems operate on vendor-locked firmware and strict uptime guarantees. Applying immediate, daily software patches to them is often technically and operationally impossible. Relying on IT departments to simply patch their systems faster is no longer a viable primary defense against automated exploit generation. Defenders must pivot to attacking the supply of bugs at the architectural level. This requires migrating critical software components to memory-safe languages like Rust, which physically prevents entire classes of memory vulnerabilities from being written into the code. For existing codebases, defenders must implement class-wide mitigations like control flow guard or hardware shadow stacks to proactively break the exploit chains that automated models rely on. The N-day patch gap previously provided defenders with a margin of error measured in weeks. In the N-hour era, security must be built into the foundation of the code itself, because you can no longer outrace the attacker to apply a patch after the fact.